can do my introduction.
Well, let me. You've got to mute. Okay, that's good. I think that's good. All right, so let's get started. In terms of the camera, welcome everybody to the TWed tonight. Thank you everybody for being here. A couple of logistical announcements. Next week's TWed, which is going to be run by Anirudh and Amit, is actually going to, unless you see otherwise through email, it's actually going to take place up in the library, the bottom floor of the library in the beta classroom. And we will be serving the pizza. It's going to be a 6 o'clock. It's going to be a 6 o'clock start up there. 5:45 for the pizza. It's going to be awesome. This is actually despite what you may have heard, this is going to be a test run of a study that they're doing. It's not going to actually be a real study. So it's going to be a normal TWed, but there are going to be some logistical stuff that they're going to work on. So it should be really exciting. And it's going to be something related to using Jupyter and Jupyter Hub and Jupyter Notebooks. It should be an excellent and very interesting talk. Sign-ups are open for what? Lightning talks. What? Lightning talks. All right. Let's get going on that. Get your spot. TWed lightning talks are a great way to end each term. I think it's in 2 weeks' time, maybe it's 3 weeks' time. Check your schedules. We're going to have the second R users group of the fall term. Those take place up in 3206 in the CII, which is near the main elevators in the CII. And the R users group is officially called R Pirates, RPI rates. Awesome. Awesome. None of these lame users with R. None of that. That's lame. We're the only college in the universe that can be the R Pirates. So that's exciting. So look forward to that. And so with another logistical thing, this is being live streamed right now. So just keep that in mind. You're welcome to ask questions at any point, but just keep in mind your questions and comments are being recorded in case you run for president. Assuming things change, you won't be able to deny any comments that you make. So we thank, Nidhi, we always look forward to your talks for TWeds. Okay. Nidhi Rastogi is going to be giving our talk tonight, an update on her work on anomaly detection. So
yeah,
thank you.
Sure. There's not this talk is not as much about results and experiments. It's more about the direction that I'm going to take in my research. So thank you everyone for joining me. The topic remains the same for my presentations, a little bit of tweaking here and there. So today it's again using information centrality, which is great because things haven't changed so much. I haven't changed my course. I haven't changed my research topic. It's just the approach that I'm taking, the tools that I'm using have, because I'm exploring different avenues, so they have changed, or I've gotten upgraded because I've changed the data sets and stuff. So yeah, using information centrality for anomaly detection in large networks, my topic remains the same. So yeah, I will not talk about the stuff that I've talked in the past two talks, TWed talks, but I can tell you, because you're asking, information centrality is an algorithm in graph analytics, which basically identifies central nodes in a large graph based on the algorithm, which is what it basically does is based on the flow of information and how nodes are connected with each other. Certain nodes are identified as central nodes. That's what. No, I can. Central nodes are, by virtue of their position, and again, there are different reasons, but in the world of information centrality, by virtue of their position and by virtue of the information, the data which has passed through them, certain nodes are more important and are able to identify or are able to detect the behavior of the network before other nodes can. So there are different kinds of centralities, like degree centrality, betweenness centrality, and the page rank algorithm is also based on the centrality algorithm. So the social network, the study of social network, a lot of it is based off of centrality algorithms. What nodes are central because of the connect number of connections they're making, which important connections are connected to which node, hence making it an important node. That's what centrality means. So these are terms coming from graph theory, and they are the ones that I'm using in my research. Okay, sure. Um, okay, so the research outline is about. I'm going through the problem statement so that you can, kind of uh, uh, get an idea of what I'm working on with the methodology, the experimental setup. More about that in the next section, which is background on NS2. I don't even know if any one of you has heard of what NS2 is about, and then the validation plan for my research. So yeah, next is the prevalent security tools are basically missing in the way that they can detect attacks, cybersecurity attacks in today's networks. And that is precise, like, what are the security tools that you usually are used to seeing? Intrusion detection tools, um, and antiviruses, firewalls. These are the ones that you're used to hearing. But at the same time, you've heard so many attacks happening, like every day you hear of so many intrusions happening, millions of databases getting into the hands of hackers. So which clearly indicates that there is always a need to match up to those kind of attacks and come up with innovative tools which can cater to newer kind of attacks, and not just the kind of attacks, the kind of data, the kind of new kind of networks that we are seeing, which are different from the traditional networks. For example, we are not just talking about enterprise networks, we're also talking about networks created by vehicles, called vehicular networks, networks created by sensors, called wireless sensor networks, and the kinds. So the main concern with the existing tools is not just because they cater to the traditional kind of networks, but also because they are not yet fully capable of detecting anomalies or anomalous occurrences, which I'll talk about in the next slides, what anomalies mean, um, and indicate that an attack is happening, because anomalies can be of any kind. We are focusing on anomalies which result in cyber attacks. So inability to timely detect anomalies, um, anomalous occurrences in networks, and that is the big data problem in cybersecurity. There's so much data, the volume, variety, and velocity. All of these lead to all of these lead to concerns in the security industry. And also because, like I just mentioned, that the threat landscape is changing, the kind of network, the kind of role that humans are playing, all of that is increasing the complexity of detecting attacks. So, like I said again, security technologies need to increase their pace.
There's one more V,
Um,
veracity. Usually,
Veracity.
veracity, which is the legitimacy of the data, whether it's the validity of the data,
That's
or
true.
the timeliness of the data, or whatever.
That's true.
So these are the classic three, and there's some bogus fourths,
That's true.
But they tend to, more and more, in particular, people like IBM, with their big data stuff, are talking about veracity as well.
It's true. It is a genuine problem, and I was reading about it yesterday that some of the nation states are what they're doing is they are introducing documents into the internet, without being without people being able to track what the sources of introducing those documents, and that those documents are covering information which may not be fully truthful or which other people were not aware of. So there are nation states which are introducing those that kind of information in the on the internet, and internet, nothing gets erased unless you do it through legal ways. Google has a cache for everything, so you are absolutely right. But is that still on a scale? I don't know. However, it's going to become a genuine concern that how do you trust what information you are you know you're exposed to? Is it
Right.
valid or not?
Yeah.
So that's true. So yes, big data, and it's all these three characteristics that lead to uh, more complexities in security, and there are different ways of addressing them. And my research is focused on addressing those via anomaly detection, which can help identify attacks because it can identify the items, events, or observations that do not conform to an expected pattern. It's very hard in large networks just because the data is it's because of the amount of data, and um, it's very hard to again pinpoint where the anomalies are if they are smaller in number. And also, if you're looking from a bird's eye view, all the data looks same. So you need to run through sophisticated anomaly. First of all, you need to understand what an anomaly is. You need to understand what your network is, characteristics of the network are in a normal day, what the operation looks like in a normal day, and then how would an anomaly be identified by what does it mean. So again, it can how do anomalies arise? They can arise through operational events, for example logs, which are generated um, from like I mentioned in one of the other bullets. They can come through the physical layer, network layer. Logs are just information about what is happening in the network. So anomalies are identified by running through those logs. Then the kind that network abuse, for example, excessive amount of data transfer uh, is a form of network abuse. End user behavior, for example, um, for example, login from an end system at odd hours, and design and implementation bugs, and can all of these are sources from where anomalies can be detected, and then collecting all that information and then making sense out of it. So these are the reasons why anomaly detection is hard, but we still address that. um, Packet collection, like I said, in depending on what network layer you are focusing on, it could be origin destination flows, like the IP addresses of where the data originated from and where it led to, where it's going to where the request came from, packet collection, and all of these, studying all this traffic on all links can result in multi-dimensional data sets, which means that should you be interested in tracking the TCP header, or just the IP address, or the port numbers, and all that means multiple dimensions of data sets. So the commonly employed approach is to seek an alternate lower dimensional approximation, which means identifying what is important to your network. Should you want to focus only on the packet size, or just the IP addresses, or just a few dimensions? That's what I'm trying to say in this point. So the newer challenges in securing large networks, basically, if we have to summarize those, it means large amount of data, increased computation, and taking a lot of time to analyze data. All these lead to um, the challenges, and that's the goal of anomaly detection, to address those challenges by minimizing it. And of my researches, can we come up with ways where data collection can be minimized, computational power can be reduced, and time to analyze can be reduced. All of that, can anomaly detection help us by lowering the dimension of the network data set? Because like I said in the previous slide, increased dimensions means too much data and too much analysis. So there's too much of many things going on without compromising capability to detect attacks. So that is the research question I'm trying to answer. So there are other ways. Going a little on the side information is, there are other ways of detecting anomalies apart from the one that I am working on, and that is just by using a threshold. For example, if the packet transfer in a network between certain computers or certain endpoints shouldn't be more than 1 GB in a given month or in a given week, that is an example of identifying anomalous behavior via threshold. Um, there is another popular technique in machine learning world called principal component analysis. I'm sorry, I forgot the analysis word here. What it does is, it reduces the multidimensional uh, multidimensional um, attribute of the data set to a fewer dimensions which are enough to basically tell you about the behavior of the network. So instead of running your analysis over hundreds of dimensions of a data set, what principal component analysis can do is, it can reduce to like 10 10 attributes which you can analyze. There are other ways called the graph traversal for finding cause and effect. Like I say here in the example, that given a graph representation of all relevant logs, it can be framed as a large scale graph search problem. So, graph analysis, machine learning, threshold, these are all these are all ways of attacking the anomaly detection problem. Um, so the hypothesis is that, and my work is going to be focusing only on volume anomalies. I figured that not every solution is meant for all kind of security problems. So the solution that I'm focusing on, which is the information centrality algorithm, it, because of the way information centrality works, it is more suitable for for identifying volume anomalies. And what volume anomalies means is identifying malicious DOS attacks, attacks which are behavior which are represented by an entire network instead of just a few subset of a network. So those are called volume anomalies, unusual end user file transfers. So knowing that what the baseline behavior of the network is not going beyond a certain threshold. So going beyond that would mean you've identified the larger behavior of the network. So unplanned outage due to router misconfiguration. So these are the kind of anomalies which are called volume anomalies. So and also existing research has suggested, studied that in other research papers, that studying data flow using graph is a useful and it is a proven technique. My approach is, however, different for identifying attacks in a network. So that gave me lot of confidence that I can go for the approach that I am actually going for. So the main idea is to use information centrality to simplify network analysis by identifying central nodes, which I explained in the beginning of the presentation, and observing the behavior of these central nodes um, in sufficient of these central nodes is sufficient for identifying volume anomalies in the network. That is what I'm going to eventually prove through my research, that just by observing the behavior of these central nodes, which are calculated using information centrality, it's sufficient to identify anomalous behavior in a network instead of running an analysis over all the nodes given network, in
So
a given large network.
is the information centrality aspect that the trying to figure out the intuition.
Sure.
um, is it that anomalous nodes are are that are volume hogs are going to be more central when they shouldn't be, or is it that by watching the central nodes, you see because they're central, you see things
Before,
you'll see
uh,
things there because they're central.
that's right. It is actually the latter. The intuition is the latter. And it cannot be the former, because in that case, you will be calculating the central nodes very, very frequently. The idea is to not do that, right? The idea is to identify the central nodes because of what the network structure is, the layout of the nodes is. And hence it is also key that the nodes do not move too much. The mobility aspect has been discounted at this point. So, assuming a large network of homogeneous nodes, homogeneously behaving nodes, um, because of the way network data has been flowing over a period of time, which means I calculate central nodes over a period of time. In a network where anomalies have not occurred, means um, I need to know the central nodes before any misbehaving node has changed the behavior of the network. So that is the idea. So now those how can those central nodes be useful in detecting anomalies of this certain kind, volume anomalies, is the hypothesis. Yeah, which is yes, they can, and just by observing those central nodes. And what are the kind of anomalies? It cannot be like every kind of anomaly. What are the kind of anomalies? And again, central nodes. Um, when I mean central node, it's like the top 5% or the top 10% of because central nodes, they are not like magical nodes. Basically mean that these are the nodes where behavior will be detected before it propagates throughout the network. So now that behavior can be detected at most on in the top 1% central nodes or the top 2% central nodes. That also I am researching what are these top in a given anomaly, kind of anomaly, uh, given number of nodes. So also understanding the behavior of the network at that time. So yeah, the approach details are yeah. So the approach that I'm taking there, I'm going to be talking about that now. The network data needs to be simplified, which means using network flows. Network flows essentially are it's uh, it's it's basically, if anybody has ever come across packet capture files that are enough to capture the network flow information, where the kind of information is basically which IP address is the source and which is the destination, what is the packet size, what port numbers were from the sending node, from the source node, and from the target node, and what protocol was used, was it TCP, was it UDP. That is the kind of information which is captured in network flow data sets. And network specification, again, using information centrality and anomaly detection, identification, and quantification. Um, the idea is to detect occurrences with high probability, identify specific time of occurrences, which means that, well, we'll talk about this soon. So the tools that I'm going to be using, this talk is more focused on that this time. The tool to create. So here's the thing. I'm going to be running my research in two environments. One is the simulated environment, and the other is closer to a real environment. So simulated environment needed to be created. The real environment, I have gotten access to PCAP files of of a real attack of nodes that were systems which were part of a real attack. So I'm going to be first proving my research idea on simulated environment, and then on the real network. So the simulated environment needs to be created, and for that, I during my research I found out that network simulator is the best tool because of the level of details you can go into it. You can create a network very close to a real network, change different parameters, and understand how a network will behave. Uh, and so there's a lot in control using a network simulator. So here are some of the more finer details about network simulator. It's called a network simulator. The current version is Network Simulator 3, but I'm still using 2 because I'm very comfortable using Network Simulator 2. So it's a discrete event network simulator for internet systems. It has been around for more than 20, 30 years. So started in UC Berkeley. It can simulate.
Yeah, this simulator has been still has been maintained by people.
Yes. Yes.
Yeah, I was at the website just the other day, and it's
The most recent version came out in 2009. Yes. And for anyone who is working on networks, they are aware of this network simulator. And it's a very heavily used tool. So when I was doing my master's in 2000, my research was in 2008 to 2009. Even at that time, it was heavily used. So I should have just begun with this tool, my research with this tool. But anyways, so the good thing about the network simulator is that as network topologies have evolved, there have been patches coming in which have catered to those kind of topologies. For example, when the wireless sensor network wave came in early 2000, they adapted to it. And now that vehicular networks are coming in, um, like Uber is running its own research, um, that kind of network can be simulated using network simulator. And like I said, you can go very deep into the protocol level. Low level programming can be done using network simulator, which gives you a lot of control and understanding before you can dive into the real world networks. So it's a really good tool, but very hard at the same time. Um, yeah. So like I mentioned here, not just the networks that it can cover. You can also simulate different kind of attacks. Um, I never done that before, but apparently you can actually run many kind of attacks using a network simulator. So, and it also has a visualization um, tool called NAM. So I felt that this was a perfect package for me, even if it required a lot of work, because it was also essential to understand how networks behave before I come up with my theories and my results. And that's the reason a network simulator was a choice. And then so some of the components of network simulator are pre-processing. You can create traffic, you can create different kind of topologies of mobile, static, all kinds of networks. And did I mention that? No. Yeah, and post processing, you can create trace files and then later on make changes to those trace files like manually, and then again see what the result looks like. So it gives you a lot of flexibility. And these are the different kind of network simulator models. Traffic models can be simulated of the web, file transfer protocol, telnet, uh, etc. And the important protocols which usually one wants to simulate, TCP. At least these are what I'm concerned with. There's much more it can do. I'm not covering all of that. Routing and queuing, wired routing, unicast, multicast. I'm not sure people are aware of that, but unicast means just single um, node-to-node communication in multicast. It's more like broadcasting, but a subset of broadcasting. mobile IP, queuing models, drop tail. So basically, drop tail, red, fair queuing are how packets are handled in when there is congestion. So these are the different kind of queuing models. I need to deal with all these details in my research. Hence, I'm going with network simulator. Physical media, like I said, all kinds of networks, wired, wireless, satellite, all of that can be modeled using network simulator. And the architecture, a bit more about that. Like any object-oriented and modular architecture, this one also allows code reuse. There are different kind of TCPs. I'm not sure about how well versed are you with networking, but they would, TCP is not just TCP. There are different kind of TCP models also. The problem which I may not be facing is that the consequences of using network simulator is this: if you like scalability comes at the cost of speed and memory, which I may not be facing because I'm not going to be running my simulations on a very, very large network. I'm going to be running it on a very small network of maybe 100 nodes. So that may not be a problem for me. The software structure, it uses C++ and OTCL, which is object TCL. C++, I know very little of C++, and that is probably the reason why I am finding network simulator a bit hard for me. So separation of control and packet level. Control is basically when before you make a connection in any kind of network, you need to transfer or you need to share. There is a handshaking mechanism which happens before the actual packet gets transferred. The packet is the payload containing the information. So that is called the control level, and then there's a packet level. You can achieve that separation. OTCL is for control, simulation setup, configuration, blah blah, and then um, the only problem is you need to learn two languages, which is okay because mine is a very small um, simulation. And then C++ is for packet processing and and reasons which you may already be aware of. And why C++ is still popular is because of fast execution and full control over execution. So it's all about control. That is what encompasses the architecture, and this is a diagram to solidify what exactly it looks like.
So you actually have to configure your simulation using C++ code. So you code it in C++.
Yeah, but like I said, I'm not very good at C++. There's a lot of off-the-shelf code that I will have to change, but there's something I have started with. So it's not like doing everything from scratch. But there's a lot of control which I need, and I just have to learn and do it. So these are the different languages which are used, and but it also gives you an idea how much of control NS2 can provide you. It comes at the cost of some work and etc. But never mind.
The most important programming language in the world 20 years ago.
It was
It was pretty C++.
C++. Oh, it still is.
Wow, no.
It still is. If you are interviewing for big companies, the top two options are C++ and Java. C++ is still really big for low level
R and
programming.
Python. Cool jobs.
In this lab. I think for data scientists and people who are dealing with a lot of data, at the application level, C++ doesn't hold much value.
What did Donald Trump say? Boring.
Next.
No.
Next.
No.
Wow.
Wrong. I'm sorry.
Anyways, I haven't seen even a single talk by Donald Trump because I'm so much into.
I hear he's fascinated about huge networks. Huge.
So here are the properties of my research test bed. Yeah, I'll be, like I said, I'm not going to be having a really large network for my simulation.
So you brought that up a couple times. Can you can you talk just a little bit about, well, several aspects, kind of unfold them.
Yeah.
Why wireless sensor networks in particular? Why 100 nodes is sufficient?
Yeah.
Why don't you need more in order to validate what you're doing? This is a good question.
So why wireless sensor networks is because wireless sensor networks, the properties of it's important to understand the properties of wireless sensor networks, and just give me 1 second. I think I covered that in this list
Okay, cool.
because
Go ahead.
that's what I went through when I was talking to Jim,
Okay, cool.
but not my 100. I will talk about that later. Um, so wireless sensor networks, how it works is it's basically capturing information. So sensor networks are like really small nodes, either like this small or maybe this big, depending on what device they are connected with or what information they are gathering from the environment or from a person's body or from a machine or like your like even a thermostat. If it is constantly calculating it's constantly capturing the temperature of the room. That is also a sensor network. So sensor networks run on batteries, which means that they have their battery life, their life is dependent on the battery, could be maybe a few years, again depending on the work that they are doing, to a couple of hours, from a couple of hours to a few years. And sensor networks don't really move too much. They're not very mobile. They're supposed to be static, and um, they're a good representation of the kind of work that I'm doing. That's why I've chosen wireless sensor networks and not other kind of networks. So my research may not be very useful, which I need to identify. It may not be very useful if they're running on computers, because there are very sophisticated intrusion detection softwares and tools and prevention tools, already existing ones, because they have high computation power. They have they because they have high computation power, and that allows a machine to run more sophisticated detection systems and prevention systems. So my work is more like focusing on Internet of Things, where there are multiple devices but low on battery life, low on energy, limited transmission and reception capability. So basically, multiple of such kind of nodes who are communicating off and on, who are not changing their position. So I cannot have mobile networks as like wireless networks. Like my work will not be applicable to those kind of networks or on cellular networks. So the kind of work that I'm doing is, uh, and the kind of nodes it will be most useful to, will be, it's closest to wireless sensor networks. That's why I'm using wireless sensor network. I hope that answers your question. Does it?
Yeah.
Okay.
That
And
makes sense.
yes, network is bidirectional, and there is application to this kind of work. Many industrial and consumer applications, they use wireless sensor networks, and uh, what else? I think I covered that. Sensor, energy resource, usually battery, yeah, etc. Now, why 100 nodes? Because I need to first prove that that information centrality is useful in anomaly detection. And if I increase the number of nodes too much, I think it may add to the complexity at a very early stage. So the 100 nodes are 1 million nodes. First, let me prove that on 100 nodes, okay? And then if and I want to study what aspects of I have multiple things to study, basically the behavior of the algorithm, the behavior of and the effect of flow of data, how nodes are connected with each other. All of that needs to be studied, so it better be done on a very small scale. So Dr. Hendler said 10 nodes are enough. I figured 10 is way too small, so I extended up to 100. And I'm not validating my research only on these 100 nodes. I'm validating on another real data set, which is like 40 gigabytes, and that has millions of nodes. So I want to study all these aspects first by having the complexity needs to be a bit lower at the lower side. That's why 100 nodes. So later on, it will be on a much larger network. And the other thing is these nodes, it will be easy for me to change the topology of the network. Again, there are multiple dimensions that need to be, there are multiple attributes that need to be studied. And it's better to start that with a smaller data set instead of having too much information to process, and uh, basically variables need to be in your control. So that's the reason. So the properties of the test bedded is yeah, that's what I go through here. Um, yeah, basically this is actually in continuation to the previous slide, properties of the research test bed. Um, the topology, like I said, that it can be from a star to multi-hop wireless mesh network. Propagation techniques between hops can be routing or or fault flooding, like multicast or unicast, etc. So yeah, all of this. And so I wanted to show you my uh, demo for the 100 nodes, but I can't because my code is not complete. So I will show you how NS2 works for wireless sensor networks, but I don't want to change this configuration. So I'll do it at the end.
You,
I will do it at the end,
oh, okay.
if that is okay.
Yeah, that's fine. I hear what you're saying.
So yeah, and so next slide is about what tests I'm going to be running with my simulated data set. So these are the things that I'm going to be studying on this simulated data set. Is study the network flow connection between various IP addresses, apply information centrality on those, prove that information centrality is better suited for volume anomalies, uh, and try different topologies, generate the location of those nodes randomly, and then the way data is flowing, is it just random direction or bidirectional? So these are what I'm going to be studying in my simulated environment. And but with the real data set, I have a separate code, a Python code, which I have already run and shown to Dr. Handler. Uh, but I'm going to be running the larger data set. Like I said, it's like 40 gig data set, and there is attacks have taken place in that network, so that data set covers those attacks also. And what I'm going to be showing is that this algorithm works for detecting anomalous behavior in that network. Um, yes, and for validation purposes, what is the goal is what should an anomaly detector be capable of? What is the goal? Diagnose anomalies observed in simulated and real data sets for various data sources and topologies. Uh, these are really important considerations. The topology of the network. It's uh, the behavior of an algorithm which is based off of flow of data in a network, that can change based on the topology, and the central nodes, they can change based on the topology, and that also needs to be proven. And how does time and location of the anomaly affect performance of the method? So the answer is so network simulator has the capability of monitoring how data is flowing between nodes, between an origin node and a destination node, and nodes in between. Compare detection on central nodes versus time of inducing anomalies. Again, another cool thing is in network simulator, you can introduce anomalies and observe how our central nodes and what time are central nodes actually detecting, and when does the anomaly start to spread into the network, propagate into the network. How many central nodes are used for graph sparsification? Like I said, I mentioned earlier, 1%, 10%, 15. What is the volume of the anomalies? How does that um, how is that a factor of the number of central nodes one needs to identify? Inject anomalies of different sizes and kinds and diagnose these known anomalies from linked data. Form this repeatedly for each time step um, and basically get a sense of how to diagnose effectiveness of the algorithm. Um, so the experimental steps would be running the network simulator on popular topologies, random node generator. I think I've covered this, so there's no novelty in this. So yeah,
Just a quick question. The so the structure of networks is not random. So when does NS2 generate the random node structure for you? How I guess what I'm asking. So I've seen simulators
Right.
that sort of simulate random, but they create networks, simulated networks, and you follow um, power laws.
That's right. Power law networks is
Oh
what it's
yeah,
called.
they because that's real. Okay, so does um, NS2 let you do that?
It can let you. It allows you to create random networks. It allows you to create power law networks. It allows you to create social networks because they have their own topologies. It allows you to create star networks or it's just how whatever you want, it will create it for you. In the simplest form, it can you can even give the exact x and y coordinates of the node. But if you don't give it, network simulator is not going to create a pretty picture for you. It's going to create a very ugly picture. Network simulator doesn't know the x and y coordinates, so you need to be writing your code in such a way that it understands. But for the popular topologies, there are already there is existing code. But again, you need to study that code if it works for you or not.
Okay, so
There
another
is no
question.
standard.
In that, so that sort of that 100 node play count you're just setting up, you um, need to model the anomaly that you're trying to find. So,
Right.
so of those 100 node, is it are they monolithic? Are they the same? Are they all wireless
Yeah.
sensors? Or are they some
Right.
wireless sensors, some servers that are getting
No.
receiving stuff? What's the distribution of different nodes?
Right now, it's homogeneous. They're all the same. I'm not focusing on the characteristic of the node. They're all the same. The capability, the bandwidth, uh, the data flow, it's all the same, exactly the same. Like I said, certain variables need to be kept the same so that I can study uh, the behavior of the algorithm.
So how do you introduce the so it's a volume is what you're interested in.
Mhm.
So how do you introduce that into
Yeah,
that
so I
scenario?
think I covered in one of the previous slides. There is something called CBR Constant Bit Rate here. It is a it is a uh, it is a feature in network simulator. CBR is what it's called, and you need to specify that between this node and this node, this is what the this is what the rate of the bit will be. Is that what the question is?
Well,
Or
so I guess what you're so in my mind would be and this is probably wrong, but in my mind, you would if you create a simulated environment, the purpose of that is sort of to introduce either problem traffic or problem nodes, things that are trying to perturb the
Yeah.
system.
Yeah.
Okay?
You're
And
right.
I think what you're saying is you would say, okay, we're going in some of these connections between nodes, we're going to introduce crazy bit rates. Is that what you're saying? And then see whether we can detect them. Is that? I'm trying to understand how you create the experimental environment where you actually observe the problem,
Right.
observe the anomalous behavior. How do you introduce the anomalous behavior into that?
So first create the network, just not just the nodes, their
Right.
location. Then identify what nodes are connected to which ones. So identify the connections between them. The connections will also require what is the bandwidth, and then what all these are capabilities of network simulator. And then you can also introduce payload. Uh, Starting from this node, broadcast data or multicast uh, for 10 seconds or from 15 seconds, this much of the like 10 gigs of or 5 megabytes. Actually 10 gigs is too much of data. And multicast capability will it actually asks how many, what is the IP addresses, what is the node name. You specify that, like n0, n1, n2. So you say that 10 nodes will be the data will be multicasted to these 10 nodes. But because I'm going for volume anomalies, I'll probably just say broadcast. So all the nodes are going to get, depending on the bandwidth or depending on the pipe between two nodes that I have specified. So that's how it starts, and that propagation starts to happen for like 10 minutes or 2 hours or 1 minute. So that's how it's happening.
Okay,
Yeah.
gotcha.
Okay.
So how do you measure the accuracy? I feel like there's like I'm not sure and that's my know about the ground truth.
Yeah, so ground truths happens before I introduce any anomaly. Okay, and I before identifying anomalies, I'm going to be running information centrality algorithm on that network. Uh, I shouldn't say network, on that graph, and just normal flow of data, without introducing anomalous behavior, without any node misbehaving. So just normal behavior, and then identify what the central nodes are. Then later on, introduce anomalies, and then see the behavior of can those central nodes. NS2 won't be doing that for me. NS2 can't do that, so there will be post processing. I don't know how I'm going to do that. I'm still understanding how to do that. Um, but there will be a lot of post processing outside of network simulator.
But
I want to create the network first.
I feel like when you apply your algorithm to keep the real data set, I mean, how do you say that the algorithm favors
Yeah, so the data set that I have received, it also has ground truth separate, an anomalous, and an attack data set. So I have that. Without that, it's not possible. You don't know what the network looks like. So it's a 3-day data set. 1 day is for ground truth, and 2 days for when the attack happened.
how does the algorithm run? Or it's not
I don't know. I haven't done it yet.
So to read the
Until the smoke comes out of the system.
to read the packet headers like TCP, UDP, the IP addresses and all that, are you using Wireshark or something similar?
uh,
You're familiar
For-
with
It
Wireshark?
doesn't even do that for us, too.
for not for NS2,
Because
and
it's just
NS2 cannot read PCAP files.
It can.
It cannot. It can generate PCAP files.
Right. So what
It's
are
a
you
simulator.
using to read
Wireshark.
them? You are using
Yes, I'm using Wireshark, but that is for the real data set, uh, which is in PCAP format, and that I'm converting to CSV because it's easier, and then my Python code is reading the CSV files, just because there is some processing required because it's such a huge data set. It's like 40 gigs, so I need to do some. I haven't done it. I've run my algorithm only on a small subset of the PCAP files. Just 1 gig takes like 1 hour or something for my code to run, and that's a lot of time.
Right, and that's why you're doing PCA.
PCA, I want to do PCA for a comparison, because how do I prove my algorithm is good, and how good? So PCA is an accepted way of identifying anomalies. it's been around for 9, 10 years, and much more refined versions have come up. So PCA, and I want to learn PCA also because it is very heavily used in the industry, and to me it makes a lot of sense also because in reality what you get is a multi-dimensional data set, and identifying what dimensions you want to focus on and capture the data set in that sense and then run your analysis of PC, I think is a good baseline for making comparisons with my work. Do you have any comments on that?
No. Also, any kind of dimension reduction kind of you lose information in that.
How that's true. You do lose information, but at the cost of, you know, the complexity reduces. You can do analysis in close to real time. If you can't do that, if the analysis itself is taking so long, what's the point in having so much data?
Yeah.
So
And
too much data, too many dimensions. So you
Well,
have to make it
if
practical.
and principal component analysis is being used properly, here it's that. So in theory, you just talk about eigenvectors, so you're not losing anything if you use all principal components. Because all they are is one. However, usually what you're doing is your principal component analysis purpose is to find the combination of the dimensions which are most significant. Right. And so, and oftentimes that's a couple of principal components. That's the magic of it. Is, if I've got 10 dimensions, I find that 2 or 3 principal components that are the vast majority of contribution. That allows that therein lies the sort of the dimension reduction. As I say, I get most of my bang out of just these 3 principal components or 2 principal components.
Yeah.
And so, translated to this, what is the combination of dimensions out of that 100 dimensions? What combination of those dimensions is the biggest contributor
Right.
to?
Yeah, and it is proven that which are the biggest contributors, and the results are compared to when you run principal component on a let's say on a small data set. Okay, if you run principal component, you need to see which are, and you have the result from all the components, and then there are principal components. The principal components result they are actually close to the result from all the components. The analysis run on all the components. That analysis has also been, I mean, I'm not saying I'm doing it, it has been proven. That's why it is a useful technique.
So maybe I would do your double.
Yeah,
You're
yeah.
about an hour.
Oh.
You should just be able to find your thing and go this. Full size.
Yeah, it's going to pop up.
This is going to launch
Yeah, it's here. Yeah, it's actually.
No.
So this time you'll be viewing only a few nodes. But this is how simulation appears. This is a real wireless sensor network. Um, Network nodes.
So can you describe what it's doing?
Yeah, so this, like I said, wireless sensor nodes, they have a range based on the capability of the transmitter and the receptor. So these circles are basically the increasing, decreasing range of those transmitter and the receptors. And this dot that you're seeing is actually packets being transferred.
It looks like a video
being
from
sent.
1982.
1982. Yeah. Wow.
Some of us are old.
Yeah, this will look much more much more interesting when I have 100 nodes. But this actually generates a trace file. Now that trace file is what I will be analyzing later on. And
So-
if you
So is the situation here that we've got
1, 2,
There's
3, 4,
S1.
6,
yeah, so
1, 2, 3.
so are those those two nodes, are they intentionally communicating with each other? So they're
Yeah, I have written it in a way that these two are communicating with each other.
and if you were able to, so you've got, let's say this was your subject matter. To calculate information centrality, are you going to, based on traffic, you're going to figure out what the
Not just the traffic, but also what nodes are connected to what nodes. What is the connectivity like?
right? Yeah, but I meant
Because in reality, it's not like 5 is connected to 0, 1, 2, 3, 4. In reality, that's not how it is.
right.
That's why a randomly connected graph or power law graph, I think, will be the closest to
Right.
real situation. Yeah. So just wanted to show you how this network simulator looks like, because otherwise it'll be no fun if there's no demo. So yeah, that's about it.
Is this simulator without your algorithm, right?
No, this I haven't
What is the
introduced.
analysis?
What this will basically tell you what node was connected to what, the timestamp, what protocol was used, TCP or UDP, how much packet was transferred, was there any packet dropped or not, and what was the range, like I said, the transmitted and the reception. It is of no value, the transmission range and the reception range for my purpose, but wireless sensor networks can do that. I can turn it off and even turn off these circles, the larger ones, showing the range of the transmitter and the receptor. So it gives all that information. And when I introduce anomalies, it will also show, it will also give me information about like the queuing models I was talking about. So this queuing model is leading to how much of packets were dropped in this given model. So all that gets captured. Do you want to see? Take a look at the trace file. I can...
Anybody want to see trace file?
It's a boring text.
So my question is, when you, before and after you use the anomaly, will the trace file remain the same regardless of the anomaly file?
The trace file is an ongoing process. So as long as this simulation is running, it keeps.
Right.
It's like a log file.
Yeah. So you mentioned that you have a ground truth before.
Yeah.
You introduce an anomaly.
Right.
And you
That's
use
right.
Anomaly. So does that trace file like the same because when you analyze not the same?
Like I said, trace file is not a static file. It's an ever-growing file. Whatever you're running, the trace file is created, and you can run a simulation that a recorded simulation if you just run the trace file.
So does each one give you a different topology of the graph?
So when you are creating the code for a network, you need to mention the topology.
So if you do that, then probably will be fixed each time.
Because even in random generation, depending on what random generator you have, what is the seed, there's only those many number of topologies which will be created. So if there's not enough randomness, you won't get enough randomness in topology. That's how it works. Okay.
Any other questions?
Of
course.
He's like, I am not done. I'm not done. You can stop.
So I'm still not really clear about the, because I know that you're working on the volume impact.
Yeah.
But when you have that slide over there, it still covers like a list of different volume.
That's true. Yeah.
But what I concentrating on, is only concentrating on the DOS attack, or you have multiple.
DOS attack is a big deal.
Is it a big
You
deal?
know that?
Yeah.
Every other day. So Dr. Heller had the same question. He was like, you need to know what attack you're focusing on. They need to be relevant today. And that day I went back home, I was on Twitter, and there was a DOS attack that day, and I sent it to him. It is relevant today. And since then, it's been 2 weeks, I had a meeting with him. I've already seen 4 DOS attacks, large scale, important, which made it to the news.
Well, the one where Krebs, Brian Krebs.
Yeah, that was it.
Within the past couple days.
640 gigabytes of attack bandwidth was taken.
It was basically, so it swamped Akamai's ability
Yeah.
to control
His website.
well, control, protect, right?
Yeah,
So,
protect.
so he's using Akamai. But this is Brian Krebs and Krebs and Securities, like the major.
Yeah, Brian Krebs is a journalist, a security journalist.
And he's, so it's hugely important. So he was, I can't remember what if they know who did it, but he was.
No, they don't yet.
He was being this galactic denial of service, distributed denial of service attack against him. Because it's a big entity, he uses Akamai as a content distribution network because there's a people following him.
So Akamai has actually offered for free to host his website because he's a big deal.
Yeah. But it was part of their service, part of their built-in service, because they have to, is protect them against distributed denial of service attacks against any content that they're serving up. This attack swamped their ability to protect, so they actually had to disable access to him because they couldn't protect. It was bringing down Akamai,
Yeah.
which is ginormous. So it was a major.
That's right.
There was a DDoS attack on the Battlefield servers. They're releasing a new game, Battlefield, and they have
So you just went offline.
I just did. Okay.
Yeah, I assume that you're offline.
I figured that why are we wasting?
Yeah, we're done.
You know.
All right, so let's thank Nidhi.
Thank you for attending.
Thank you very much.
Next time there will be results. For sure.